right, so now we're back to n. Okay, so let's say there is a note recorded as the notion of the so-called dot product. For vectors in Rn that is defined as follows. You have two vectors u with entries u1 through un and v with entries v1 through vn, vectors in Rn. Then u dot v is defined to be u1 times v1 plus u2 times v2 plus up to un times vn. This is a scalar, of course, and in matrix form, you can view this as the transpose of u matrix multiplied with the vector v or the matrix v. Okay, so geometrically, the importance of dot product is the following. Suppose you have your u and v sitting in this position, and there's an angle here in between them called theta. Then u dot v is the length of u times the length of v times cosine theta. And here we remember that the length of u is actually the square root of u dot u. Okay, and likewise for v. Okay, so this geometric point of view tells us that the dot product can be used to measure the angle between two vectors. In particular, it can tell us when the angle is 90 degrees, right? Just keep in mind that cosine of 90 degrees is 0. And that means the following: the two vectors u and v in Rn are orthogonal or perpendicular if the dot product is 0. Okay, that's the definition. That's in R2 it's easier to see this. In Rn you want to work with this as a definition. Okay, so now we can consider, we're going to consider the following notion. So suppose I have a set of vectors u1, u2 up to up, a subset of Rn. This set is called an orthogonal set. If each pair of distinct vectors in S is orthogonal. Okay. In equations, this means ui dot uj is 0 for every I not equal to j. Okay. Let's look at some example. see the following collection of three vectors: 1, 1, minus 1, 0, 1, minus 2, minus 1, 0. Okay, these three vectors are vectors in R4, and let's call them U1, U2, and U3. And to decide whether this collection is an orthogonal set or not, all you have to do is to compute the dot products of any two of them. Right, so U1.U2, U1.U3, and U2.U3. Okay, and that's a straightforward computation. Each of these is a straightforward, however lengthy it may be, computation to do. Okay, U1.U2 would be this expression, and that's equal to, well, this is 0 here, is 0 there, it's 1 minus 1, so that's 0, fine. Good. For U1.U3, you're looking at 1 times 1, 0 times negative 2, 1 times negative 1, 2 times 0. You're still looking at 0 here and 0 there and 1 minus 1, so still 0. Very good. So for U2.U3, 1.1, 1 times minus 2, minus 1 times minus 1, 2 times 0. So you still get a 0 here. Then you have 1 and minus 2, so that's a 0. Fine, so orthogonal. Okay. Now you can come up with various examples. So this is, for example, the easy one. And let's look at a very general one. Consider the following collection of vectors: 1, 0, 0, 0, 1, 0, 0, and so on, up to 0, 0, 0, 1 in Rn. Okay, remember these are what we've been calling E1, E2, and so on, E. And each of the, say, EI has entry, i's entry being 1 and other entry is 0, right? EI takes this form. This is the i's entry. Okay, so now I want to claim that this is an orthogonal set. And to see this, I just need to compute the dot product of EI and EJ. And now you see, well, let's, for the sake of discussion, use the matrix description. Okay, so the dot product should be this matrix product. And the point now is that this first, or this row vector, is the transpose of EI. So the 1 here, the only non-zero entry, occurs in the i's place, whereas this column vector here, which is just EJ, has the non-zero entry occur at the j's place, right? And if you form the matrix product, if I is not equal to j, then this 1 and this 1 will not meet each other. This 1 from i's entry will multiply to a 0. this one from the jth entry will multiply to a 0, and all these other entries at 0 multiply to zeros. So the dot product is therefore 0. Okay, and this is true whenever I is not equal to j. So you have therefore an orthogonal set. Very good. This is very general. Now, one nice thing about orthogonal set is the following. So let's suppose we have a collection U1 through UP of vectors in Rn. Suppose it is an orthogonal set. Then it is immediately linearly independent. Okay. So that's it's a nice thing to have, and it's fairly easy to prove. So we'll do that. So consider to determine whether the collection U1 through UP is linearly independent or not, we have to study this equation. And we want to argue that the only way for this equation to hold is for the C's to all equal to 0. Okay. So let's do this. Here's what we're going to do. We take the dot product with UI, where I goes from 1 up to P. Okay, and that will give us the following. And on the left-hand side, I'm dotting this linear combination with UI. On the right-hand side, I'm dotting 0 with UI. So I immediately know what I get. On the right-hand side, that has to be 0. On the left-hand side, we're going to use a distributive property for dot product to write it as C1 U1 dot UI plus C2 U2 dot UI plus stuff plus CP UP dot UI, and that's still equal to 0. Now, over here on the left-hand side, all the terms are 0 except for the ith one. So these guys, this dot product U J dot UI is 0 unless J is equal to I. Right, being an orthogonal set, we have uj dot ui equal to 0 whenever j is not I. When j is I, you're having ui dot ui. So the only term that's not 0 on the left-hand side is ci ui dot ui, and that's equal to the right-hand side, which is 0. Now, on the other hand, this thing here, ui dot ui is never 0. This is not 0 because the vector is not a 0 vector. So we are therefore forced to have Ci equal to 0. And this discussion is true for every I. So that means the only way for this linear combination to equal to the 0 vector is if all the coefficients, the C's, are 0. And that's what we call linearly independent. Okay. Very good. Okay. So now what we've seen. We've seen that orthogonality implies linear independence. Right? That's what this theorem says. Now, the notion of linear independence was used in various places, in particular in the notion of basis. That's one of the requirements for being a basis. And in fact, now we can consider the key definition that we want to formulate. Definition. A basis, and also normal, orthogonal basis. Orthogonal basis of Rn is a basis of Rn that is an orthogonal set. Okay. All right, so again, the notion is just the notion that we're defining is called orthogonal basis, and it's simply a basis that is also an orthogonal set, which means that the vectors in this basis are pairwise orthogonal. Now, suppose we have an orthogonal basis U1 through UN. Okay. Sorry. In fact, there's no reason to work to demand that this is a basis of Rn. Right. So we should change this to W. W here is a subspace of Rn. Right, so this should also be W. Okay. Try again. So we're defining the notion of an orthogonal basis of a subspace of Rn. An orthogonal basis of W, a subspace of Rn, is a basis of W that is an orthogonal set. Now, suppose you have such a basis, consisting of U1 through UP. If these vectors all have length 1, then hold on. Okay, it's not working somehow. Oops. Whatever I wrote seemed to have disappeared. I'll pick up from where we left. So the definition was that an orthogonal basis of W subspace is a basis of W, which is also an orthogonal set. Okay, an orthogonal basis. Now, if you have an orthogonal basis of W, say U1 through UP, be an orthogonal basis of W if the lengths of these vectors U1 through UP are all equal to 1, then this collection U1 through UP is called an also normal basis. Okay, so the word is a little different here. This word normal here just refers to the length of these vectors being 1. Okay, so now we have two kinds of bases for subspaces of Rn. One is called orthogonal basis. It's just a basis consisting of pairwise orthogonal vectors. If in addition that these vectors all have length 1, then such a basis is called also normal basis. Recall that orthogonality implies linear independence. Right, that's one theorem that we worked out moments ago. Also, the number of vectors in a basis is equal to the same number for any basis. That's called the dimension, right? So for orthogonal or also normal basis, for orthogonal basis, so if we have the dimension of W vectors that are pairwise orthogonal, then they form an orthogonal basis. Okay, and because if you have the correct number of elements for being what you need to be a basis is one of the two conditions, right? You just need linear independence or spanning, but being orthogonal implies linear independence. So therefore, you're guaranteed to have orthogonal basis in this condition. Okay. Now let's look at some example. The first one is the ones that we've just seen, a very general setting. And we know these guys, this E's, as vectors in Rn, they form a basis of Rn. EI is, as you recall, the vector with ith entries being 1 and 0 everywhere else. So this is, we've seen that it's orthogonal, and we already knew it's a basis. So this is an orthogonal basis. So, well, before that, there's something else to say. Right? If you compute EJ dot E, if you compute the length of EJ, not EJ, EI, you will see that the length of EI is EI dot EI, taking square root, which is 1, because EI dot EI is 1. And this is true for every I. So you have a collection that's pairwise orthogonal, and it has the right number of elements, and every vector is of length 1. So this is an orthonormal basis. Okay. Now, let's consider the third thing. Sorry, the next thing. Say you have 3 vectors in R3. These 3 vectors. I mean, R3 has dimension 3, so having 3 vectors is certainly a good thing if you want a basis. Let's call these guys V1, V2, and V3 respectively. Then we can compute, the following. We can compute their dot products, V1 dot V2, V1 dot V3, V2 dot V3. Okay. V1 dot V2 is 3 minus 2 minus 1, 0. V1 dot V3 is 1 minus 8 plus 7, still 0. V2 dot V3 is 3 plus 4 minus 7, still 0. So this is an orthogonal set, and the fact that it has 3 elements, which is the dimension of R3, means that you get an orthogonal basis. Right? Now, these vectors are not of length 1, because you can just check what the lengths of these vectors are. V1 dot itself is 1 plus 4 plus 1. So that's square root of 6. V2 dot with itself is 9 plus 1 plus 1. That's 11, or the square root of 11, being the length of V2. V3 dot with itself is 1 plus 16 plus 49. It's 66. Right? Well, none of these is 1. So what we have here is not orthogonal, is not also normal basis. Okay? But if you see that the only thing that fails for these 3 guys to form an also normal basis is that these vectors are not of length 1. So if we just rescale these vectors like that, And this is, now these vectors have length 1. And this is an also normal basis. Okay. And in fact, what we just did, namely rescaling these vectors, is something that we can do in general. So suppose you have U1 through UP, and also orthogonal basis. Okay, suppose that's the case. Then any multiple, non-zero multiple, if you multiply the vectors U1 to UP by any non-zero number, you still get an orthogonal basis. Right? That's just because AI UI dot AJ UJ is AI AJ times the dot product of UI and UJ, which is still 0 for every I not equal to J. Okay, very good. So if you now choose these A's to be the length of these vectors U's, or the inverses of them, that is, you consider U1 divided by the length of U1, U2 divided by the length of U2, and so on. And this is an also normal basis. As we've already said, this is still orthogonal basis. Now for each I, the vector, the length of this vector, ui divided by the length of ui, is computed as follows. Ui dot, ui divided by the length of ui, dot with ui divided by the length of ui. So it's ui dot ui divided by ui, the length of ui square. And remember what the length of ui is. It's, well, the square of that is ui dot ui. So we really have ui dot ui divided by ui dot ui. So it's 1. Okay. Very good. So it's not hard, therefore, to go from orthogonal basis to an orthonormal basis. All you have to do is compute the length of each basis vector and divide the basis vectors by its length. Okay, so that's not hard. Now, recall that when we have a basis, B, say W1 through WP, when we have a basis of W, again, W is a subspace of Rn. And every time we have a vector W in W, we can write it as a linear combination of the basis vectors A1, W1, A2, W2, AP, WP. And these A's, namely the coefficients of these linear combination, these guys are called coordinates of W with respect to the basis B. And if you put them in order into a column vector, this is called a coordinate vector of W with respect to B. All right. We had this. So now the next thing I want to talk about is that if the basis B above is an orthogonal basis, then the process of determining the coordinates for any given vector W is simplified, or well, not simplified, it's rather simple. Then for W equal to A1 W1 plus A2 W2 plus AP WP, we have the following thing. Okay, we can take the dot product with Wi for each I. On the left hand side, we will be looking at W dot Wi. On the right hand side, it will be A1 W1 plus A2 W2 plus AP WP dot with Wi, which is the same as A1 W1 dot Wi plus A2 W2 dot Wi, and so on. AP WP dot Wi. And because the little w's form an orthogonal set, this W1 dot Wi, W2 dot Wi, and so on are all zero except for Wi dot with itself. So the only term that's left on the right hand side is this AI times Wi dot with Wi, which tells you that AI is W dot Wi divided by Wi dot with Wi. Okay, so this is therefore telling you that if the basis is actually an orthogonal basis, then it's fairly easy to compute the coordinates of any given vector in terms of dot product. Okay, so let's see some example. See here. Say I have 12 minus 3, 6, 1, 2, 1. No, I don't want this. Just want the previous example, 1, 2, 1. 3 minus 1 minus 1. 1 minus 4, 7. We've argued that this is also orthogonal basis. Okay. So let's call this guy V1, W1, W2, W3, respectively. And let's say we have V. It could be anything, but for the sake of simplicity, let's consider this vector. And again, so we know because the W's form a basis of R3, this V can be written as a linear combination of the W's. And we are interested in finding the coordinate or the coordinate vectors of this V with respect to, call this guy B. Okay, we're interested in that, and we've discussed how to do that in general, right? All we have to do is take our V, dot with each of the W's, right? According to our discussion, the coordinate vector of V with respect to this basis B is computed this way, right? Then we can be more explicit about what this answer is. You'll just take a moment. So it's 1, 4, 1, and 6 down here. So what is it? So it's 12 minus 6 plus 6, so 12. Okay. So this one is 9, 11. 9, 1, 1, 11. Yes. 36 plus 3 minus 6, 33. And so for the last one, W3, I have 49, 50, 66, and 12, 24, 42, 66. And of course, the numbers are chosen so that the outcome is simple. Okay, so this is an example of how we apply the previous discussion to find coordinates for any vectors with respect to an orthogonal basis. Okay, good. And now the big question is, of course, how to find, or rather construct, an orthogonal basis. Right, we know how to go from orthogonal basis to an orthonormal basis. That's an easy part. So the question is how to construct an orthogonal basis to begin with. So there's a general process called the Grinch process. Okay, and the setup is this. So W is a subspace. Let's say the dimension is P, and the process requires as input a basis to begin with. Okay, say you have a basis W1 through WP. Then define. Then we get now we get then the following vectors. Let's call them U1, U2, UP, is an orthogonal basis of W. Okay, so what are these U's? U1 is W1. U2 is obtained from W2 by subtracting something. U1 dot U1, U1 W2 dot U1. Okay. U3 is obtained from W3 by subtracting the following things. U1 dot U1, U1, W3 dot U1 minus W3 dot U2, U2 dot U2, U2, and so on. In general, Ui is constructed from Wi by subtracting the following quantities. Oops. UK dot UK, UK, Wi dot UK. K goes from 1 to I minus 1. When for every I bigger than 2 or less, but less than or equal to P. Okay, this is certainly very complicated looking. So well, the proof is not very hard, right? Because once you know the answer, proving this just requires that you check the dot products at 0. Okay, but so let's spend some time thinking about how to construct this guy. Why? So you start with these W's, W1 through WP, and you want to build out of this a basis that's orthogonal. So you have to start from somewhere. So let's just declare declare the first vector to be W1. And now I want U2. And now I want the next vector, U2. I want it to be at this point I haven't constructed anything beyond U2, beyond U1, right? What I want is U2 dot with U1 to equal to 0, because I want an orthogonal basis, or I want an orthogonal set, so I want the vectors to be pairwise orthogonal, and I have U2, so I need it to be orthogonal to U1, and I have to build U2 from somewhere, right? So again, I start with W2. So I would like U2 to be orthogonal to U1, so I want it to be from W2 plus some directions along U1, and I want that to make that happen. Okay. So, but if these two things are imposed at the same time, you know how to determine this A here, right? Because you want U2 to take this form, W2 plus the multiple A times U1, and then you want U2 dot U1 to equal to 0. If you dot this equation by U1, you get U2 dot U1 should equal to W2 dot U1 plus A times U1 dot U1, right? And you want this to equal to 0. You want this to equal to 0, and that forces you to have A to equal to negative W2 dot U1 divided by U1 dot U1. Okay, and this is this answer here is indeed what we put here for the definition of U2. Now what do we want next? Now let's consider the next vector. U3. I want U3. I want to build U3, right? What the conditions do I need? I want it to be orthogonal to U1 and U2. And I have to build U3 from somewhere, so I want it to look like it's going from W3. So so we would like to have U3 being of the form W3 plus some combinations of U1 and U2. And then we can impose the condition that U1 and U3 is orthogonal to both U1 and U2. U3 dot U1 will then be W3 dot W1 plus B U1 dot U2 U1 plus C U2 dot U1. And we impose the U3 dot U1 to equal to 0, and we already by construction get U2 dot U1 equal to 0. So this is forcing us to have B equal to W3 dot U1 divided by U1 dot U1 altogether negative. And it's certainly what we see here. Okay. And if we dot the equation, if we dot this expression with U2, we have U3 dot U2 equal to W3 dot U2 plus B U1 dot U2 plus C U2 dot U2. And again, we impose that U3 dot U2 equal to 0. And U1 dot U2 is by construction 0. So this forces us to have C to equal to negative W3 dot U2 divided by U2 dot U2. Okay, and this is again, oops, try again. Negative W3 dot U2 divided by U2 dot U2. This expression is again what we wrote up here with the negative. Okay, so and we can do this in general. In general, we want I to look like Wi plus something A K U K, K going from 1 to I minus 1. And we want Ui dot Uj to equal to 0 for every j less than I. Right? In other words, we inductively construct these U's. We can, when we have U1 through Ui minus 1 constructed, we use it to construct Ui. and require that ui be perpendicular to u1 through ui minus 1, that condition. Okay, so this is what we want. And if that's what we want, then we get the following. When we take ui dot uj, so when we dot the equation for ui with uj, we get wi dot uj plus sum ak uk dot uj, and then we can just proceed like what we did before. We impose the condition that ui dot uj is 0, and for each j here, j is less than I, so uk dot uj will only be non-zero for one term, k equals to j. So this expression here is just aj uj dot uj. So that means ak is negative wi dot uj divided by uj dot uj, which is what we wrote here. Oops. Never mind. Okay. So good. So, and you see that this process, this inductive construction, produces vectors at each step being perpendicular to the previous vectors. So therefore you get an orthogonal set, and it has the right number, so it's an orthogonal basis. Okay. And right, so now let's let's stop here for now and pick up from here next time, so that we remind ourselves a bit more about this process, and also look at some examples. Okay.